This is sections 9.2, part 2. So as we recall, we talk about the series and the sum of all the terms, and we have the first test called divergent test, right? Then we have the second type of test is called the telescoping series. Now, let's look at another example here. If you look at this series, 1/2 to the n, and we look at the sum of all the terms. Okay. Now, again, you may want to write out the first few terms to get a feel of what the terms look like. Okay. So if I'm looking at, let's say, what's the first term, a1, right, and it's 1. So plug 1 in, you got a half. Second term is 2, so 1/2 squared, it's 1/4. The third term is 1/8, 2 to the third. The fourth term is 1/16. And the fifth term is 1/22. So if you look at these terms, it's 1/2, and then the next one is 1/4, and then it's 1/8, then 1/16, etc. Right? Now, first observation is a term. The following term is half of the previous term. Now, the term is getting smaller and smaller. So the question is, if you continue to add all of these, it will add up to what? Is it finite or is it infinity? This is the only example that I can show you intuitively what the answer would be. Okay, so other examples, we might use some tests to prove it, but we just don't get the feel, and sometimes it goes against your intuitions. Now think about it this way. Here is the geometric interpretations. Let's say start out with this square, right? With size 1, right? So this square has area exactly 1, right? So if I cut this in half, okay, cut this in half, what do we get? Right, so this side has area 1/2. Now the remaining 1/2 divided by 2, right? So this is a quarter of the square. The remaining quarter, you cut it in half. So half of a quarter is 1/8. So this area is 1/8. The remaining 1/8, again, you take half. So that's 1/16. Remaining 1/16 divided by 2, you got 1/32, etc. Keep going. 1/64, and then going, keep going, keep going. If you keep going, you see that we're going to keep adding all of these smaller area, and it will end up to the original square we started with. So the area of the original square is precisely 1 unit square. It's 1. So the answer here is 1. So we say this infinite series converges to 1. All right. But again, how do we do that? Now, again, this is a very special case. If you have 1/3 to the n, or if I change any of these number, you won't be able to see nicely how the geometric area that actually show you the sum. So we must have a way to do. Like observations earlier, the following term, it's always half of the previous term. Notice that we don't have to have exactly 1/2. But this is a special case. As long as you have a series where this term is basically time 1/2 to get this next term, and time 1/2 to get next term, time 1/2 to get the next term. So in a series, when the following term is equal to the previous term times the same constant, then that series is called a geometric series. With, now think of it the other way, so instead of times, you're gonna have, you form the ratio, so that's over this, this over this, this over this. If you take the ratio of two consecutive terms, that ratio will be 1/2. That's why this is called the common ratio. Right, so here's the definitions. In a geometric series, each term is found by multiplying the preceding term by the same number r. Right, so it will look something like this. You start with the first term a, you type r, you get ar, type r again, ar squared, ar cubed, and etc. Now, in the compact form, using sigma notations, that a times r to the n minus 1, and solid 1 and infinity, right? So plug 1 in, you got this, plug 2 in, you got this, etc. Right? Now, if you recognize that it is geometric series, then this series will converges if the common ratio less than 1 in absolute values. So what it means is it could be negative, right? If you have negative half, it's fine, but absolute values of the common ratio is less than 1, it will converge. In fact, it will converge to this number, a over 1 minus r. A is the first term, and r is the common ratio. And it will diverges otherwise. That is when the absolute of r greater than or equal to 1. Okay. Let me show you again the example, the previous example here, right? So you can recognize that's a geometric series. Okay. And that's a geometric series with the common ratio 1/2. Notice that the original, the time I have to get the next term. The original term, the first term here is also 1/2. So from this example, what do we know? That is a geometric series. Okay, when I say geometric series, I need to specify the common ratio r. In this case, it's 1/2. Since I had 1/2 to get the next term. And what is the first term here? 1/2, right? So the a is also 1/2. A is 1/2. R is 1/2. Happen to be the same. It doesn't have to be the same. Okay. Now, according to the series, this geometric series, notice that the common ratio here, right, if you take the absolute, if you take the absolute values of r, or in this case it's 1/2, it's less than 1, right? So it's 1/2 less than 1. So the series that we consider. So that is the one we're looking at, 1/2 to the n power infinity converges. Now, not only do we know it converges, but I know that it's the sum must be a over 1 minus r. And we get what's a? A is 1/2. The common ratio is 1/2, right? So subtract 1/2 here. And then the numerator is the common ratio. It happened to be 1/2, right? So let's do the math here. It is equal to 1/2 the numerators, right? 1 minus 1/2 is 1/2 the denominator. Well, 1/2 over 1/2, it's 1. Right? So it is precisely 1. So it is 1. So that confirmed the answer we got earlier, isn't it? That one? See that the answer is 1. Right? So from now on, we can use this geometric series test to determine whether zero converge or not. Okay. Now let's look at this one. All right, so is the next example. So let's say we're looking at one. Right, -6 over 5, blah, blah, right? So test is a series that convergent and divergent. Well, one way to do is if you can put it in that form. Normally, I don't like it. You see this one here? You give a something to n minus 1 power. If you can put it in that form, it is geometric series. For this case, let me do it this way. Since I noticed that -6 to the n minus 1, right? So, and then 5 to the n minus 1, so I can rewrite that as -6 over 5 to the n minus 1 sum from 1 to infinity. See that match the form that we have a r to n minus 1. And then you see that this is what a geometric series. It's a geometric series, right? With when you say geometric series, be sure to say what is R, what is A. R, see, -6/5. What is A? A in this case is number in front, well, it's 1. Okay, so now identify the geometric series, and then look at that the absolute values of that ratio in this case is absolute of -6/5. 6/5. And this is positive 6/5. And because of positive 6/5, it's more than 1. So the series, we can include the series diverges. Okay, right? So according to this one, the absolute of R is greater than 1, it's diverges. Okay. Now, I'm going to skip the middle one and look at the so let's say label number 2. Now this series is written in the expanded form. You can put it in some series sigma notation if you want, but you don't have to. Again, if you want to test for the geometric series, this is your first term is 1/8. That is the second term is -1/4. Positive half is -1. Okay. So one way to think about this is, if it is geometric series, can you know what number I multiply 1/8 to get -1/4? So what do I multiply? Right. So if you time, you see that's positive 1/8, that's negative. So it must have a negative. Okay, so time -2, right? Time 2, and then 2/8 is 1/4. And you can check again and multiply -2 from -1/4 to 1/2. Times -2, you got this. And then see a time the same number, -2, to get the -1, right? -2 times 1/2 is -1. So since I multiply one term to get the same number to get the following term, this is a geometric series. And again, geometric series, identify the common ratio R, the same number that we multiply -2, and the first term is 1/8. However, the common ratio in this case is absolute, well, the absolute of -2 here is +2, bigger than 1. The series diverges again. Okay. All right, so let's move on to the last example here. The last example we're going to do is about converting decimal numbers or fractions decimal numbers. We know that if we need to convert fraction to decimal, right? So that's easy. If you have to do that, say 7 to decimal, right? How do we do that? Just do long divisions, and then you got the decimal numbers. But sometimes we convert the other way around. Well, if you convert, say, 0.42, right, to fractions, it's actually easy because you read this number is 4,200, so that's 42/100 is simplified. You got fractions. Now, what is hard is when you have the numbers, the decimal number that is repeating decimal, right? Say 4.2222. So how to convert that to fractions? So we're going to use ideas of the geometric series. Now think about this. If you do, let's say, convert 1/3 to decimal, well, I think a lot of you know by now it's 0.3333, go on, right? Or sometimes we write 0.3 bar. Now let's say we don't know this, like this one, you don't know how to convert to fractions, right? So if I give you, hey, this is 0.3 bar, right? So that's 0.333. Can you convert that to fractions? Okay, so what do we do? Now we can think of 0.333 here as a sum of infinitely many terms, and they all have pattern. So what do it mean? Right, so 0.33333 is the same as 0.3 plus 0.03 plus 0.003 plus 0.0003 plus. Just want to see that, right? So 3, and then you add the 3 here, the second decimal place, and the third, and the fourth, and keep going, right? So now you turn a number into an infinite series, okay? An infinite series, okay? So here's what we're gonna do. You see the number here, 0.3 bar, right? It's the same as this. And then from here, I can recognize that, well, how do you get the next term? This one is 3/10. That is 300. That is 3,000. Okay. Again, the answer is a third, but for now, pretend we don't know yet. Okay, so it's not a problem. I don't know the answer yet. I'm trying to convert to a fraction, the third. So what I'm going to do is think of this as fractions. Well, each of these I can turn into fraction, right? So that's 3/10. That one is 300. That is 3,000. The same thing, that's 3/10,000. Now, from here you can see, to get the next term, I multiplied by 110, isn't it? Time 110, time 110. So I can identify that this is indeed a geometric series with what's the common ratio? 110. Right, multiple 110 in the next terms. And what is A? What's the first term? E is the first term. 0.3. Right? So what we do next? We check the absolute value of R. In this case, absolute 110 is 110. You see that is smaller than 1. So we know the series converges. Converges. So that means the sum is finite. And the sum would equal to, so these, to A over 1 minus R. Right, 2A over 1 minus R, the formula we have. And again, A is what? 1.3. Or, I think if you wish, you can convert to 3/10. Since this is 110. I'm not sure you want decimals and you want fractions. Actually, we do want fraction because we want to convert to fractions for these problems. So why not turn that into 3/10? So A is 3/10. Okay. Right, so A here is the 3/10 over 1 minus the 110 is the R. Right, so you simplify, right, that's A, that's R. 110, 1 minus 110 is 9/10. Okay, then you have 3/10 over 9/10. I can really cancel the 10. So that's really 3/9, right? Or 1/3. Okay, see, that's how we convert decimal to fractions. Okay, that's really finished the 9.2.